Right, I've finally been able to upload the document and it's easy to read. I've been having so many technical difficulties with this particular video, I can't tell you, but hopefully this should be fine now. We're going to carry on with this question. In a second experiment, the current is adjusted so that the weight of mass, 15 grams, is raised at a constant speed. The motor is connected to a 6-volt supply, and it now takes the motor 3.4 seconds to raise the weight through 0.84 meters. Suggest how it might be determined that the weight is being raised at a constant speed. For this to be at a constant speed, the best thing to do would be to measure out successive distances, the mark scheme says, but that means any 10 centimetre or something similar, but measure those 10 centimetre distances. How long does it take the weight to cover those 10 centimetres once, and then to do it again for the next 10 centimetres? That time should coincide if the object's moving at a constant speed. Okay, so the answer would be any sensible distance which would be easy to measure. Timing, how long it takes the weight to cover that distance, and each time it covers that distance, it should take the same amount. Determine the power delivered to the weight by the motor. The acceleration of freefall can be considered to be g equals 10. Okay, now power is simply work over time, work being the energy transferred. In this case, it would be kinetic to gravitational. The weight is going up. So if you can work out what the increase in potential energy is, then you could work out the power by simply dividing that increase by time. To work out the gravitational potential energy, we would use mass times g times the change in height. So if we add in the values that were given in the question, then we have for the increase in potential energy, we have 0.015 times 10 times 0.84, and that gives us 0.13, divided by the time that takes, which is 3.4 seconds. So the power, finally, is 0.037 watts. The next question is about efficiency. What is the efficiency of the motor? Well, efficiency is a ratio of the power out to the power in. We're looking at an energy conversion here. The energy in is electrical. The energy out is gravitational. Now we know what the power out is because we've just calculated it. I know I've given you this as energies. The efficiency could be energy out, over energy in, or just as easily, it's interchangeable. You could have power out and power in. So I mentioned energy here, but it could just as easily be power. So we're going from electrical power to gravitational power. We know our gravitational power, but what is our electrical power? So we still need to do some sort of a calculation. Now previously in the question, we were given the voltage, 6 volts. And now suddenly we're given the current, 45 milliamps. If we remember from the previous section, power, electrical power, is equal to current times voltage. So we can now work out the electrical power that's given in. Current, 45, times 10 to the minus 3 times 6. That gives us 0.27 watts. So if we go back to what was explained here, we can now work out our ratio. The power out over the power in will be equal to the answer to this question, 0.037 over 0.27, which gives us 0.14 or 14%. Okay, this question is just another application of Fleming's left-hand rule. We have an electron travelling in the direction shown and entering a uniform magnetic field. So first of all, trick, it's not conventional because it's a negative charge. So this left-hand rule becomes the right-hand rule. Number 2, check the directions. Previously, we had a question where the direction of the charge moving was in the same line as the field. That was a trick question, because then, of course, it's 0. Here, everything's fine, because they are, in fact, perpendicular. So now you just have to use your right hand for the left-hand rule replacement, and you should be able to see that the answer is B, out of the plane of the paper. This should be a fairly familiar question now. 2 long vertical wires, X and Y, carry currents in the same direction and pass through a horizontal sheet of card. Iron filings are scattered on the card. Now you should remember that the iron filings were those the same as the ones we used when we were looking at bar magnets. And what they do is they show you very clearly what the field lines around a bar magnet will be. So it's asking you which one of the following diagrams shows the pattern formed by the iron filings. So which picture will show you the pattern, the field line pattern around these 2 wires? Now we know that the field line patterns around a wire are concentric circles. These are 2 parallel wires, so they're either going to attract or repel. So we'll just do a quick test to see which one it is. Okay, so this is a bird's eye view. If we draw the wires and then use the right hand corkscrew rule, you can see that if the wire is coming, the current is coming up, the field lines would be concentric circles going in this anti-clockwise manner. And similarly, the one next would also go in the anti-clockwise manner. And you can see that the arrows are going against each other. So you will have an area here where there is no force acting. So let's have a look and see which option gives us that. Here we have field lines, yes. Field lines, yes. These are field lines, but not for a wire. These look like field lines and charges. I'm not really sure what that looks like, but nothing familiar. Okay, so it's down to these 2, and this, they both show a space in the middle, but this one's actually showing that in the center there would be a force acting, so it must be A, because here is where the forces cancel out. So the answer is A. Okay, a lot of information in this one. We have a charged particle of mass m and charge q travelling in a uniform magnetic field with a speed v. So the magnetic force is F. So we have F equals B, Q, V. The magnetic force on this particle of mass 2m, then what would subsequently be the force if the mass is now 2m, the charge is Q, stays the same, and it's travelling twice as fast. So if we add that in, it would be B B stays the same because it says here it's travelling in the same direction in the same magnetic field. Q is the same. And 2V. Mass isn't in this equation, interestingly, so this is a bit of a confusing addition. Well, what have we got? We've got a force that is twice as big. Now, it's not easy to disregard this m. You have to look really carefully to see if there's some other aspect to the question. But there isn't. Okay, so this is a really straightforward answer, B. Okay, this is getting a little bit repetitive, but it just goes to show just how common this question is. The diagram below shows two parallel vertical wires, each carrying equal currents in the same direction. The wires pass through a horizontal sheet of card, and diagram 2 shows you a plan view. Draw on diagram 1 the direction of the force acting on each wire. Now this is a really sneaky question because it's saying it is like a free body diagram in a way because it's asking you to draw the force acting on the wire. Now first I'm going to draw the field lines to show you how this force is acting. So these are our field lines, and once again you can see that this area in the centre is an area where the field lines cancel. Now because there is an absence of field lines, what happens is that the wires end up being pulled towards each other. So you would now then need to apply this to the first diagram and show them pointing in. Now the field line pattern that we see is being asked for as part of number 2, draw the field line pattern due to the current in the wire. This is not enough. You need to show the resultant field line pattern, which I'll try and draw in a different colour. Okay, if we draw resultant field lines, they would look like that, the field lines in blue. Okay, and if we draw arrows, they would go in the same orientation as the black lines, but with a space there in the centre. In effect, looking something like this, but a lot better. Because this contraption doesn't let me draw things neatly. Hopefully you've done this to show a nice circular path. Now some extra things to take note of. You must be careful drawing these field lines because you must show how the field lines show the strength. So really you need to show field lines getting further apart as they're separated from the source. Okay, so this distance must be bigger than this distance. And this one must be even smaller. Oops, made a right mess of that one. Okay, so if you have a look at the mark scheme, there's a perfect representation of this diagram. So don't lose easy marks, okay? You need a good shape. You need to show arrows to show the direction. And you also need to show the strength with the separation. Field lines, when you're drawing field lines, you always need to think about the separation and the strength. Okay, this is one of those horrible waffly IB questions. Let's have a look if we can make some sense of it. The card is removed and one of the two wires is free to move. Describe and explain the changes in velocity and the acceleration of the movable wire. So this is our bird's eye view from the top of the wires. So one of them is free to move and it starts to pull closer together. Now as this wire gets closer, the effect of the forces on each other increases. So it will accelerate because the force increases. And if its acceleration increases, then its velocity will increase. Okay? So change in velocity and acceleration, well, force increases, so acceleration increases. And if acceleration increases, then velocity must increase. Okay, last one. A current-carrying solenoid is placed with its axis pointing east-west, as shown. A small compass is situated near one end of the solenoid. The axis of the needle of the compass is 45 degrees to the axis of the solenoid. The current in the solenoid is then doubled, so the strength of this increases. Well, if we think about the field lines follow the same pattern as in a bar magnet. Okay? As the strength of the field, if this solenoid becomes stronger, what would happen would be that all of these field lines would become closer together. Now, the best way to think about that is if you have a stronger field, then your lines or the amount of lines per unit space would increase. There'd be more field lines. And you also know that the strength equals the distance between the field lines. By having more field lines, they would have to, in order to not cross over each other, they would have to pretty much just tend towards the vertical at the poles. So what would happen is this orientation would become closer to the axis of the solenoid. So the answer would be B.